Before going further into the topic, before going further into the topic, let me quickly revise the terms properly. I suggest you, everybody, take pen and paper as well, okay, or at least have a book and pen so that you can do it simultaneously along with me. So it is more of a writing thing, so that you will also be able to revise the terms properly. Clear, everybody? And if possible, everyone, please switch on your videos. Yeah, let's see this now. See, when we discussed, while we were discussing about thermodynamics the other day, I told you that uh, thermodynamic is mostly mm, macro macroscopic view. So it is not a microscopic view, it is more of a macroscopic view. Correct. Second thing, we have various types of systems, and we learn within the system we had open type, closed type of system, and isolated system. Open system as in where there is an exchange of mass from the system. Okay, so that could be between the system and surroundings, there is some exchange of mass. At the same time, there is an exchange of energy also. When it comes to closed system, there is no exchange of mass, but there is an exchange of energy. While isolated implies that there is no change in mass, there is no change in, sorry, energy. This is isolated system. Clear? So I think the basic terminology you are aware of. Okay, next. Right. Next thing we need to understand is what is thermodynamic equilibrium. This is another important term I told you. To measure anything like a state function, we need to always attain thermodynamic equilibrium. Okay, clear. In simple terms, what it meant is that it is a macroscopic property of a system where there is no change, where there is no change of pressure, temperature, and concentrations of matter in the system. So when system has a certain constant pressure and temperature and concentration remains constant, right? Then we say we have achieved a thermodynamic equilibrium. Got it? Clear. For example, let me show you with an example. In a chemical reaction is happening. Imagine there is a chemical reaction happening. have calcium carbonate, which is in equilibrium with calcium oxide and carbon dioxide. Okay. Although I know that you haven't learned anything about equilibrium, I'm just giving you a brief idea that equilibrium means a reaction is possibly happening in the forward direction as well as the backward direction with the same rate. Then we say it is under equilibrium. Okay. Now, if you compare uh, what are the total number of phases here, correct? How many different phases we have? So what I can say, number of phases. Phases are the small change in the state, any change in the state here. So you can see there are mainly two states here, isn't it? So if you notice the calcium carbonate and calcium oxide, they are in the same phase, that is solid state. In fact, they are in the same state, solid state, and carbon dioxide is in gaseous state. Clear? But is it necessary that calcium carbonates, which is looking like a solid, will be having same density as calcium oxide? No, right? So the state is same, but the phase is different. Correct? Phase always imply the kind of boundaries that you draw might be different. Here, this might be more, hollow. Sorry, this might be more solid and it might be more denser. But when it comes to calcium oxide, it will be more hollowish because carbon dioxide is coming out of it. So it does not have exactly the same solid nature. It will be more like a semi-solid form. So then I will say there are total three phases in this reaction. Got it? Clear. Now, in that case, this solid, gas, and solid, all these three are at a different phase. Okay. Now, as long as there is some measurement that you are doing, that is pressure calculation or uh, temperature calculation, whether you are performing any calculation, if the number of phases remains constant, then we say it is at an equilibrium. This is maintained at an equilibrium. Got it? And if we emphasize this part, I told you that as long as pressure, temperature, and concentrations are constant, then we will be able to measure them and we say this system is at thermodynamic equilibrium. Got it? The system is at thermodynamic equilibrium. So, whenever we say that there is a thermodynamic equilibrium, what are the three types of equilibrium we'll notice? One is physical equilibrium, which means between system and surroundings or within the system, there should not be any movement of uh, boundaries. There should not be any movement of boundaries which might change the pressure. Okay, so that is called as physical equilibrium. So as long as physical equilibrium is concerned, we expect that the pressure comes to a constant value. Pressure is constant. And then we have thermal equilibrium. And when I say something is at thermal equilibrium, we expect that the temperature is coming to a constant value. And lastly, material or um, material or chemical equilibrium. This is when the concentration of material is constant. If that is not changing, then we say it. Physical equilibrium can also be used as mechanical equilibrium. So mechanical or physical or same. Clear? So as long as these three equilibriums are achieved, we say it is under thermodynamic equilibrium. Okay. So I hope all of you remember this part. that when we discussed what is thermodynamic equilibrium. Okay, then right now, whenever we talk about system, surrounding, and boundaries, let me remind that also we started off with this ideology that there is always a system present, and outside we have surroundings, and this entire thing is a part of universe. Okay, so in short, system is a part which is under observation, which we are able to see it, we are able to understand what are the changes that are happening. Okay, and surrounding is something which is, away from the system, where certain boundaries are being met, and overall whatever the system and surrounding is, that is universe. Correct? Right. Now we learned also what are the boundaries. So when it comes to boundaries between system and surroundings, that could be real or imaginary. And when I said real, again we had two kind, which is uh, diathermic and adiabatic. Adiabatic. Diathermic means which conducts heat. The material or the wall that is being made by the material is something which can conduct the heat, or here it does not conduct heat transfer, and here it conducts heat transfer. That is the other simple difference about boundaries. This is something which we learn next. When it comes to types of energies, what are the types of energies that you will observe in thermodynamics? Okay, so we will come across the term work, heat exchange, sound energy, light energy. Correct, isn't it? Light is the same as radiation energy, or sometimes the terminology this is used, radiation and so. Okay, now these are very useful for many types of energies which we'll come across. Okay, is that the only energy? Well, no, that we do have other forms of energy that includes internal energy, which we represent by U, then enthalpy, another form of energy, which we represent as H, Gibbs free energy, which we represent as G, and entropy, which is not exactly energy, it is energy per unit Kelvin. So it is energy form but per unit Kelvin. So these are most commonly used energy terms other than work, heat, sound, light, radiation, and all of these terms. Got it? Now, we came across other term known as macroscopic properties. Macroscopic properties. These properties are again categorized into two forms. One is um, intensive, the other one is extensive property. Got it? So I told you about intensive means which is independent of amount or quantity. Independent of amount or quantity. Then we say it is intensive. intensive property. Similarly, we have extensive, which implies it depends on amount or the quantity that we are taking. Now, notice this when it comes to intensive, what other type we learn? Okay. Well, if I recall, pressure, temperature, all concentration terms which we learned in mole concept, molarity, molality, normality, percentage weight by weight, percentage weight by volume, okay, gram per mole, anything of this sort, volume strength. You will come across this in redox reaction, volume strength, and ppm, correct, ppb. So wherever you see these type of concentration terms, those are all intensive properties. Okay. A part of it, we have surface tension. Got it. Sorry, surface tension, surface tension, which is used as force term. Then viscosity, coefficient of viscosity, refractive index, mu, EMF of the dry cell, okay, EMF of the dry cell, and many more. Correct. These are mostly intensive forms. Next, extensive properties. Extensive as in anything which is energy based. So if it comes to energy terms, it definitely depends upon how much is the quantity that you are taking. That defines how much energy it has. For example, if it comes to internal energy, entropy, enthalpy, A represents Helmholtz energy, G represents free energy, pressure, sorry, free energy, and then we have uh, mass, only mass, volume, right? Well, density belongs here. So these are all the terms that you come across. Okay. Even moles. Okay. Now, in case if at all I try to divide intensive by extensive by any other extensive property, you'll always end up getting intensive part. Got it? So which means if you have intensive property divided, if you have extensive property divided by extensive property, it would always lead to an intensive property. Got it? That's why whenever we write UM, SM, HM, GM, the M represents per mole. So it is internal energy per number of moles. Okay. HM, which is enthalpy per mole. Correct? Mole is normally represented by N. So yeah, like this. So this becomes now the per molar unit. So per molar is always going to be an intensive property. Clear? And we did came across an important term known as heat capacity. That will be very useful here. So let me introduce here itself. Heat capacity is about how much amount of heat that is required to raise the temperature by 1 unit. Okay. So heat required to raise temperature by 1 unit, right? So for example, if at all I take C, small c, write it as small c. Small c is equal to, imagine there is some amount of heat that is given to raise the temperature of delta T. Then the units for this would be simply joules per Kelvin. In that case, this C is extensive because Here the heat release depends upon how much quantity of the matter you are taking. But then we have specific heat capacity. Specific heat capacity. This time the definition is the same. That is heat required to raise the temperature by 1 unit per 1 unit of mass. So per 1 unit of mass. So which means it is normally represented by S, which is Q divided by M into delta T. Okay. So now you notice that Q was actually the heat, which is extensive property. M is now extensive property. Both are being divided. So that makes it again intensive property. So S now becomes, sorry, let me write the units first. Units would be joules per kg per Kelvin. And now S will be intensive. Similarly, I have another term known as molar heat capacity. This we would keep on coming multiple number of times. So the entire definition is the same, except instead of mass, now it is for moles. Okay, per unit of mole. So here we write it as Cm, capital Cm, Q by N into delta T. Or simply the heat will be equal to Ncm into delta T. Now let me just copy this here. Same thing. But this time molar heat capacity at constant volume. Suppose if at all I am doing this at constant volume, then what will be the condition of at constant volume? Everything else is same. So it is molar heat capacity. So we write it as CVM. CVM. This is at constant volume. So write it as constant volume. Most of the time, instead of using CVM, we simply use it as CV. So this becomes a formula. Remember that heat given at constant volume will be always equal to NCV into delta T. So as we go ahead, start remembering formulas one by one, starting from here. So molar heat capacity, everything at constant volume. Now, if we do the same thing, but if we find out the molar heat capacity, but this time at constant pressure. Now we are doing it at constant pressure. So this is CPM now, CPM here, and we simply write it as CP. This is CP, and Q will be QP. So QP, QP, and QP. So please make sure you guys are comfortable with these four terms. And if you have noticed, CM, CV, or CP, all of these are intensive properties. Correct? Everybody? These are all intensive property. Now, what are the units for this one? Units for CP or CV will be equal to same as the above. So that is joules per Kelvin per kg, sorry, per mole. Per mole. Okay. This is the units for CP or CV. Okay. Next. So here it also tells us that if you have an extensive property, I multiply with an intensive property, I should always get an extensive property. Correct? It is one and the same. For example, if you have Cm is a intensive property into number of moles, that is extensive property. If I multiply that, then I'll get this as heat capacity, which is extensive property. Sorry, heat. In this case, I'll get this as heat capacity of the total moles. So because this value always depends on total moles. So total moles is always extensive, and moles, as it increases, the heat capacity will also increase. Got it? Now, another important factor we need to note here is that when it comes to intensive property, we cannot add them directly. Okay? So intensive property cannot be added. Intensive variables cannot be added, or they are not additive, but extensive extensive or additive. Extensive or additive. Okay. In simple terms, I can do it this way. For example, I have a compartment here. Okay. Left side, I have a pressure P, volume V1, temperature T, number of moles N1. Right side, I have P, V2, T, and N2. Imagine if I remove that compartment, if at all I remove that compartment here, what is the final pressure? What is the final temperature? But when it comes to volume, I can say it is V1 plus V2, definitely. Number of moles, I can write it as N1 plus N2, correct? But we cannot say the pressure is equal to P1 plus P2 or 2P in this case. We cannot say that, right? So intensive variables cannot be added, but extensive variables can be added. Got it? So extensive, intensive, some of you have messaged me whether, sir, please explain intensive and extensive again. So please check again. If there is any problem with this particular area, you can discuss with me once again. Anna, is that clear, beta?
Yes, sir.
Latisha?
Yes, sir, clear.
Sa?
Yes, sir.
Right. Vinayak, I think you joined new, right? So are you getting this, beta?
Yes, sir. I'm
Right. Hmm. Ah, let me go ahead. We then discussed if at all we have to calculate certain parameters when a thermodynamic equilibrium is achieved. There are mainly two parameters that we will usually measure. One is state variables and path variables. State variables and path variables. Okay. State variables means it only depends upon what is its initial condition, what is its final condition, right? So state variable implies that it depends only on initial and final condition, okay, or final states. Let's say I have a gas or any matter, it could be solid, liquid, anything, any matter, and it has a certain pressure P1, volume V1, number of moles N1, temperature T1, clear, internal energy U1, H1, clear, G1, S1. These are all its, state functions at a point A. And as it starts changing itself to a point B, where it has pressure P2, volume V2. Let's say we are not changing the number of moles. So number of moles are same. Temperature is T2, internal energy is U1, U2, enthalpy is H2, G2, S2, all of this. Even if one of this variable is changing, then we say it is a new state. Okay. So you could notice that there are so many variables that are changing, but I'm not worried from A, how did we reach B? That's not our job to worry, especially for these parameters. For these parameters, you need to worry what was there initially and what is there finally. You should not be worried about what is happening in between. How was the journey? No, that's not important for these variables. Okay. Right. Next, when it comes to path variables, okay, path variables, they depend on the path which they are taking. So we cannot say that uh, we will be able to measure at all the positions, but we can definitely say the path will change the overall value difference. Okay. For example, the value of the variable depends on the path taken. I told you the other day about work, right? Taking a stairs to reach upstairs, any maybe second or third floor, let's say. Taking stairs will consume, or you would be working much more as compared to what you will do by taking an elevator, right? So therefore, work is a sense of path variable, isn't it? And same is the heat. See, remember this, work and heat are not exactly energies. They are mode of energies, right? That means they are a mode of transport to make the energy to move from one place to the other place. Okay. So work is energy. What it is a form of energy, but it is not exactly an absolute energy part. It is about how you're transferring one form of energy to the other form of energy by taking a path. That's why it is called mode of energy. Clear, everybody? So when it comes to internal energy, what do you say, free energy, these are all a part of a system. The system is holding it. We cannot say, hey, a system is holding W work. Correct? We cannot say gas is holding this much amount of work. We cannot say gas is holding this much amount of heat exchange. See, this is one important difference between physics and chemistry. In chemistry, we study that heat exchange as capital Q. Okay. Here we learn it as small q. The definition wise it is same. But there we say sitting it outside the system. In physics, we'll sit outside the system and observe the system. But in chemistry, we are a part of the system and then we are seeing whether we are losing or we are gaining. We are becoming a part of the system and then saying things. Okay. So keep that in mind. That is a major difference here. Clear? So yes. Now, when it comes to um, state variables, like I said, pressure, temperature, volume, internal energy, all of these are state variables. Okay. But now notice delta P, delta V, delta T, delta U, delta H, delta G, delta S. These are neither state nor path variables. So this usually becomes confusion sometimes. Okay. So do remember that. So we are saying that it is not exactly path function, it is not exactly a state function if we are talking about the change of it. Clear? Right. Correct. And second point, what I said is work and work and heat. Work and heat energy is not property of a state. They are not property of state. Okay, they are only mode of transport or mode of energy transfer. Sorry, they are modes of energy transfer. Very important point, guys. Write and learn, everybody. Okay. Can we can you guys just think about a minute about what could be the common things between heat and work? What do you think there are commonalities between heat and work? Think.
Same unit.
Hmm?
Same unit.
Same unit. Okay. In fact, all energy terms have same units. Correct. But specifically, we are emphasizing more on the path variable, right? So if you think in terms of path variable, both of them are path variables, correct? Imagine if both being path variables, does they have anything in common? Now, first common thing, what you know, both these going to be appearing only at the boundaries. They are not a part of system. It is only going to appear at the boundaries. That means if a boundary is shrinking, a boundary is enlarging, that means an expansion or a compression. When these kind of things happen, then only we say work is done, right? If there is no change in the volume of a system, that means there is no pushing of boundary or shrinking of boundary. In that case, we do not talk about work. Isn't it the same thing we do it for heat exchange also? We'll only use that heat exchange part when it is going into the system or out of the system, because heat is transferring, right? It is either coming into the system or going out of the system, and that depends on the boundary and the nature of the boundary, whether it is diathermic, whether it is real, whether it is imaginary. So that means work as well as heat, which are both mode of um, heat energy transfer, they both actually depends upon boundary conditions. Clear? So remember that. That is another very important factor, that work and heat, work and heat have common characteristics. They have common characteristics. That includes um, happens or appears. Let me put it more this way: appears at the boundaries. They only appear at the boundaries. Okay. Okay. Now they can change. They can change inside the state of system. So that means, let me put it this way: if heat is outside, in outside the energy factor, we are assuming like a heat, that I have to push it inside. Hmm? After it went inside, now you may not define something as heat. It is actually helping in converting the system's internal energy, isn't it? Same is the case with work. When work is done on the boundaries, so it is taking away energy of the internal energy and then converting into work. So work and heat helps in interconversion of various variables, energy variables. Energy variables includes internal energy, enthalpy, free energy, Helmholtz energy, entropy. All these factors, it will help in interconverting, right? So they can change inside the state or they can interconvert. Clear? Lastly, they produce they produce equivalent and opposite, equivalent and opposite effects in at the surroundings. Sorry, in the surroundings. In the surroundings and system. Do you remember I told you something about the convention of, convention that we use in chemistry, right? What is the convention that we use? The convention is simple. In chemistry, you are a part of system. So then anything that is coming into the system is always positive. Anything which is going out of the system is always negative. So I told you that work done by the system is by the system. Then work done is negative. Heat heat released by the system, heat released by the system is negative, correct? And it is done on the system. It is done on the system, clear? Then it is going to be positive. So I'm sure you guys remember the convention. Hmm? Okay, so this point becomes very important while solving problems, everybody. Now notice this one. That is, if Q of the system, that means from the system, let's say it is positive, let's say 5 joules, then definitely it implies that the surroundings heat that is lost is also 5 joules. So from the surroundings end it is -5. While if system is, let's say, making loss of, system is working on the surroundings, right, by the system, then work done of the surroundings will always be equal to 10 joules. Got it? So the loss of system is a gain of surrounding and vice versa. The loss of surrounding is a gain of system, and it always follows for heat and work. But can I say the same thing for change in free energy? That, let's say, change in free energy is 30. If the change in free energy of the system is 30 joules, can I say the same thing, that the surroundings loss is minus 30 joules, right? Then answer is no. We cannot say this, no, because it is a state function. It does not depend upon the path function. More importantly, we can talk within the system as long as we know the states of it. But what is happening in the surrounding, we can't comment directly like this, because it is not necessary to make any changes on the boundary only, right? It is not some kind of an exchange that is happening between system and surroundings internal energies. Okay. So this is the intrinsic details of state function and path function, guys. Sorry, mainly path function. State function, of course, we have a lot to discuss. Okay, how do we derive the state function and so. But yeah, but I guess all of you got this idea about path functions, right? Hmm. Now let's see what is the main essential criteria for state function. Essential criteria for state function. And for this, I told you already, okay, that we need to see three mathematical aspects into it. Okay. First one is this cyclic integration. Please understand, a lot of you have asked this doubt to me. Sir, what exactly this is? Please derive it and help me out. So I'll derive it carefully and make it very, very easy for you as well. So please check it. Understand this carefully. Cyclic integration involving a state function. A state function is equal to 0. Is equal to 0. For example, U, G, H, S, A, these are all state functions. So integral, you have to put this circle of du, integral dg, integral dh, integral ds, integral dA is equal to 0. That integral, this 0 sign represents cyclic. Because they are state functions, it has to be always equal to 0. Clear, everybody? Right. Okay. What was the second condition, everyone? Second condition is the state function are exact differentials. Exact differentials. Okay. Exact differential means, suppose for a function which depends on xy variable, then df, any change in that function can be attributed to df by dx at constant y into dx plus dou f by dou y at constant x into dy. This is called exact differential. Let me show you with an example. Okay, proof. So I'll try to help out the proof with an example here. So please check it out how we can see. Imagine I have internal energy U is equal to, let's say, 30 plus PV. This is how it is dependent on. Some equation is given to you. Acha, if an equation is given to you, what can we say? That this function is this U is a function of P and V. You can say that, right? Because obviously you can see P and V seems to be variables and U is actually dependent on these two variables. I guess this part is clear, everyone? Right. So now notice what we can say. Imagine there is a small change. For small change in pressure and volume, then what would happen? If there is a small change in pressure and volume, what will happen? Let's see. If it is a small change, let's say I have U1, because obviously if pressure and volume are changing, definitely U will also change. But 30 looks to be a constant value, so that will not change. But D of PV, this is what will happen. And D of PV can be written as, P, there is a small change in pressure and there is a small change, plus or minus change in volume, right? That can be written as, PV plus VDP plus PDV plus DP into DV, correct? And the dp into dv is extremely small value multiplied by extremely small value. So obviously it does not make any contribution to the overall u. So I can write it as u1 is equal to 30 plus pv plus vdp plus pdv. I could write that. And what was sorry, I'll take this as u2 beta just to put that different. The first one was, let's say, u1. Now, what is the difference? Du will be equal to u2 minus u1. Du will be equal to u2 minus u1. And u2 minus u1, if you notice, 30 plus pv, 30 plus pv, this will get cancelled. So what is left? vdp plus pdv. This is what is left, right? Since you have already learned the calculus, now I can do the same thing using basic calculus also. This is the algebraic way of writing it. So what is the calculus way? If you have u1 is equal to 30 plus pv, as per calculus we learn that any small change can be used as a differential. So du will be equal to, this is a constant, differential of constant is 0, plus pv, differential of pv will be vdp plus pdv. Isn't that what we got? Correct. So this is exactly we got, right? So whether you write in a differential form or whether you write it in an algebraic form here, so what do we get? The change in that uv will be equal to vdp plus pdv only. Okay, clear? Now imagine this one. What if at all I differentiate that only with respect to p? Now here, this one, I am differentiating only with respect to p at a constant volume. And you know that if the volume is constant and I define only with respect to p, then what is left? Correct. So only v will be left, right? Because v into p will be there. So differential of p dp by dp is 1. This one is 0. Similarly, if I write dou u by dou v at a constant pressure will be only equal to p. Correct? Constant pressure, it will be equal to p. Okay. So now what can I write about du? Check it out. What can I write about du? So du is equal to vdp. Okay. What do I write v as? V I can write it this way. So therefore, dou u by dou p at constant volume into dp plus dou u by dou v at constant pressure into dv. This is how we got that equation. Clear? So this suggests that u is a function of p and v. Okay. And if you are able to write this exact differential form, that means it is a state function. The u is a state function. Everybody, I hope all of you have followed that. Right. Now I told you there is another way of looking into state functions. What is that? Euler's theorem or Euler's formula. In calculus, you'll be using this a lot. In maths, you'll be using quite a lot. Okay. As per Euler's theorem, if we can write the differential function, which is df is equal to dou f by dou x, sorry, dou x by dou f by dou x at constant y into dx plus dou f by dou y at constant x into dy. This is what we can write it as an exact function, right? Now, if at all I'm writing that as differential, can if we able to write this way, the dou of dou y into dou f of dou x at constant y and this entire differential at constant x, that should be equal to dou by dou x of dou f by dou y at constant x, and this is at constant y. Okay, so in short, if you write it in a double differential form, this is what you write: dou square f by dou y into dou x is equal to dou square f by dou x into dou y. Correct? And actually, this is what you learn in calculus. Both of them mean the same thing. Whether you first differentiate that with respect to x and then you differentiate with respect to y, or first you differentiate with respect to y and then you differentiate with respect to x, it does not make any difference. You should get same value. Okay. This as a sort of example I took the other day, right? As let's say ideal gas equation. For an ideal gas equation, I can write volume is equal to nRT by P, and I need to prove that the volume is an state function. So if I want to prove volume is a state function, then what will I do? I'll do this one. Dou dou V by, you know, uh, dou V by dou T at constant pressure. First, I'll differentiate that. So that will become nR by P. Second, I'll differentiate this as dou V by dou P, at constant temperature. Then it will become nRT by minus P square. Sorry, the minus will not. So minus nRT by P square. See, I'm going with the fact that you are comfortable with this kind of differentiations already. Yeah, everyone? Right, check. Now, if at all I differentiate this function with dou of dp, then what would I get? Dou v by dou t at constant p, isn't it? And this all should be done at constant temperature. So in that case, it will be uh, nr by p square with minus. And here, dou of dou t into dou v by dou p of t at constant pressure, that will be equal to minus nr by p square. So you can see both of them are giving exactly same values. Both of these are giving exactly same values. You can see this value and this value, they are same. So that concludes that a volume is a state variable. So I suppose you learned how to derive a state function, or how to prove that there is an existence of state function. So these three are the conditions which we typically use. Okay. Is this one. Next. What are various laws in thermodynamics? Mainly, thermodynamics draws by four laws. First one is called zero zeroth law. Okay. So zeroth law is usually applicable when you have something as a thermal equilibrium. That is, let's say, if there are two systems or one system and one surrounding. Let's say if A is system, B is surrounding, or A and B, both of them are system connected to each other. If there are two systems and they are in thermal equilibrium, and if they are in thermal equilibrium, and then there are two systems B and C, then that is also in thermal equilibrium, right? Clear? So A is in thermal equilibrium with B, but B is in thermal equilibrium with C. Then it implies that A and C has to be in thermal equilibrium. Okay, this will be thermal equilibrium. So which means if temperature of A and B becomes equal and B and C becomes equal, we say that temperature of A and C are equal. This is transitive property, if you remember. Okay, so the transitive property of temperatures is what we call it as the zeroth law. Okay, then we learned about the first law. Okay, first law is referred into many different forms. It is basically energy conservation principle. Energy conservation principle. We are trying to point out that energy is conserved. It is neither created or not destroyed. It might be transferring from one form to the other form. That's it. Okay. Right. So what we say, any change that happens internally, which you call it as internal energy. In physics, we use the terminology E. In chemistry, we often use U. That should be equal to heat exchange and work done. How much is the heat exchange and work done? Okay. So here U or E represents internal energy, internal energy. Q represents heat, you know, flow into the system. I'm taking a positive value of Q, which means it is into the system. And W means, okay, uh, work done on the system. Again, I'm taking a positive value. Work done on the system. So if I take a positive value, then this equation will have everything positive. So this is positive, positive, and this is positive. Okay. I told you about internal energy. U or E. Internal energy delta E is equal to delta U, which is equal to Q plus W. Now, here, internal energy is anything that consists of, molecular, translational, rotational, vibrational, electronic energies, everything. So, for that piece, the other day I defined this as summation of all sorts of kinetic energies and summation of all sorts of potential energies that it possesses. This is about internal energy. Okay. So, one can never calculate, one can never measure internal energy of a system. We can only say theoretically we can calculate a bit, maybe, but sorry, theoretically we can calculate the change in internal energy, but not absolute internal energy. Okay, correct. Now tell me, what is the energy of the universe, everybody? Can I say energy of the universe is constant? Right? Isn't it? Is there any, whenever I say energy of the universe, we are living in one particular universe which has a constant energy. Correct? Internally, there are things changing, but overall energy is constant. And if that is constant, what will be the change in universe energy? Universe energy is zero. Got it? So, which implies universe energy means it is a system energy as well as surrounding energy. Correct? So, therefore, I can say delta E of the system, that means internal energy change of the system, is equal to internal energy change of the surroundings. Got it? Earlier, when I told you that when it comes to path function, right, you are not equal, but delta you are equal. Got it? Because whatever the loss of the system has to be gain of the surroundings. Got it? But it should be delta UL, not U. Internal energy cannot be related, but delta U can be related. Clear? Now, whenever we discuss about internal energy, or in fact any thermodynamic variable, we always learn about four uh, systems. One is internal energy, which is a standard system. Then is sorry, one is a ideal gas, which is a standard system. Then we have real gas, then solid state and liquid state. Okay, so we will always try to figure out how these variables vary in these four scenarios, in these four systems. Okay, so starting with first, internal energy, internal energy of an ideal gas U, of an ideal gas U. Okay, you know that delta U is equal to delta of kinetic energy plus delta of potential energy. Now, problem is for ideal gas, change in potential energy is zero. That means there is no change in potential energy. In fact, there is no uh, strong interaction, or in fact, there is no interaction between the particles in the ideal gas. So, which makes the potential energy, change in potential energy to be zero. If that is zero, then delta U will be equal to delta of kinetic energy. Correct? Delta U will be equal to delta of kinetic energy. Now, this is where let me introduce something called, okay, this we haven't done it. This is something which we'll be doing today, okay, known as equipartition, equipartition theorem, equipartition theorem of kinetic energy. Okay, what does that mean? See, if we have x, y, z as the coordinates, and imagine there is one particle present in space, and this all thing are a part of system only. Within the system only I'm talking. Within the system, I designated some x, y, z. That means I created one Cartesian coordinate. Within that, imagine I have a particle. And if a particle is moving from one location to the other location, let's say from here, this is at A position. Now it has moved to point B. This is the position where it has moved. Correct? So then we say this particle is moving from a position A to B. It says that the particle is translating from one position to the other position. Okay. So that means it has a kinetic energy which is helping in changing its coordinates. Correct. If kinetic energy is changing its coordinates, right? So which means this particular position from here A to B as it moves, we say there is a change in translational kinetic energy. Okay. So kinetic energy total will be equal to kinetic energy of the translational part plus kinetic energy of rotational part plus kinetic energy of vibrational part. Okay. Now, one thing we can notice that if a particle is moving from A to B, we can say it is getting translated. Okay. See, if a particle is translating from position A to position B, right, it is changing its coordinate. X, Y, Z coordinates are changing. X1, Y1, Z1. It is changing to X2, Y2, Z2. Correct? Now, there is a certain assumption on which we have to go. So, imagine if there is a particle which is completely spherical, like a ball. If you have a ball, okay, imagine like a ping pong ball first, table tennis ball, everybody. Imagine more like a table tennis ball. If a table tennis ball is moving from one position to the other position, okay, how much do you see that energy which is transferred from the bat or from the racket is been making helping it to spin? Rarely, very less amount of energy. Majority of the energy will go only into pushing that ping ball from one position to the other position. Is that right, everybody? So अगर आपने imagine करो, you have sent some energy or you have put some energy on the ping pong ball. So that ball is translating from your board to the opposite court. Correct. So majority of the energy was into translation. And since it is spherical, right? Sphere will hardly use any of the energy to convert into spin. Very less amount of energy. Now think about cricket ball. Correct. If a good spinner is bowling, clear? All we have, let's say Washington Sundar is bowling, and he's an off spinner. He's bowling this way. So out of his entire energy from its arm as it throws, how much energy he's spending on spinning? Can I say very small amount of energy is using? Right, everybody? Majority of its energy is coming from here, not from here, right? This energy is very, very less. Majority of the energy is coming from here, so that he has to throw it all the way. So can I say that for a circular, for spherical, not circular, for spherical particles, rotational kinetic energy hardly contributes to total kinetic energy. Does that make sense, everybody? Second, if that spherical particle is an atom, like a noble gas, best example is noble gas. Imagine like a noble gas. If a noble gas is moving from one location to the other location, right? Does one particle of noble gas, right? That is one atom of noble gas. Does it have any vibration of its own while moving? No, right? The particle will simply move like this. It's not like the atom is shrinking, enlarging, becoming smaller, bigger. Will it go like this? No, right? The atom is this size, it is moving with that size only. So, everybody, for a single atomic species like noble gas, will there be any vibrational contribution? No vibrational contribution. So, for single atom particle, okay, no vibrational contribution, vibrational kinetic energy contributes to total energy or total kinetic energy, correct? So kinetic energy of or kinetic energy total for ideal gas particle. See, ideal gas particle, we always assume like a point mass. Point mass means the particle is like a sphere. Then that should be equal to only kinetic energy due to translational. So there is no contribution of rotation, there is no contribution of vibration. It is only because of translational. Thus, can we say that kinetic energy total is equal to translational kinetic energy? And do you remember when it comes to when it comes to kinetic energy of the ideal gas, we have calculated it already in gaseous state, and we got that as 3 by 2 nRT, correct? 3 by 2 nRT as a total value. And if we write it for kinetic energy per particle, which we call it as average kinetic energy, per particle, we got this as 3 by 2 kT. 3 by 2 kT. This is what we got. Now, I'm sure you remember whenever we say a particle is here, correct? A particle is here, it is at a coordinates x, y, z, 1, 1, 1. Here it is at coordinates x2, y2, z2. Then as a vector r, if this is a vector r, this is vector r. How do I write r here? A vector r can be written as summation of x, y, and z, correct? This is how we write. So if this is how the vector we will be writing, then I can say that since it is 3 by 2, the overall value of kinetic energy is 3 by 2, I can say that the kinetic energy at a point A will be equal to kinetic energy in x direction component. Of course, kinetic energy is not vector sum, but I can write it as kinetic energy in y direction plus kinetic energy in z direction. These are the contributing factors, isn't it? Or what we call it as components in vectors. Let's say these are the magnitude components in x, y, and z. So here this is 3 by 2 kT per particle, and here is the assumption that we are assuming on an average, because it is an average, we can say on an average it must be kT by 2 in x-axis, kT by 2 in y-axis, and kT by 2 in z-axis. This much on an average is contributing. Okay, and this is what we call it as equipartition of energy. That means we are assuming that whatever the total kinetic energy which is coming is contributing equally in x component, in y component, as well as in z component. Okay, so therefore we can say how much amount of, you know, uh, energy that we are getting it here. So k by 2t. Now remember, if you recall, right, I'll just recall that here because we have discussed this again. Constant at constant volume, right? Heat capacity is defined as QV by N into delta T, or QV is equal to NCV delta T. Now, if I were in your position, first I will listen to the entire concept and try to re-derive on my own. This is what you are supposed to do as well. Okay. So try to understand everything first, this part, and then you redo it again. Okay, I'll give you some time. Check. So QV is equal to NCV dt. Now tell me, if at all I take the thermodynamics first law, delta U is equal to Q plus W. I told you that this work factor is only possible if there is some expansion or a compression. But if your system is at constant volume, will this be contributing factor here? No, right? So I can say that this factor is not contributing at constant volume. At constant volume. This is as per thermodynamics first law. So delta U will be equal to QV, and QV is equal to NCV delta T, isn't it? This is what you will notice. Delta U is equal to NCV delta T, right? This is what you would notice. So from there, I can say that since, now let me go get back here. Since the kinetic energy, change in kinetic energy, right, has to be change in the total kinetic energy here, right? So therefore, we can write delta U, which is equal to change in kinetic energy, right? If at all I write this in terms of kinetic energy change, I can write it as, uh, 3 by 2 nr into delta t. nr into delta t. Now, if at all I equate this to ncv delta t, n will get cancelled. So what are we getting? I'm getting cv is equal to 3 by 2 r. cv is equal to 3 by 2 r. Everyone, you guys got this? What is cv? cv, I'm getting it as 3 by 2 r. So which means how much is it contributing? That is 3 by 2 r. It is the total amount of heat capacity contributed. How much it is contributing from XYZ direction? So I can say CV, which is equal to 3 by 2 R, can be written as R by 2, which is coming from X direction, R by 2 coming from Y direction, R by 2 coming from Z direction. What is this R by 2? R by 2 is the contribution of energy when it is translating, isn't it? Can I say that or no? R by 2 is the amount of contribution of energy when a particle is translating, which means this particular form, right, that there is a certain contribution of energy in one direction. This measuring is what we call it as the degree of freedoms. Now let me introduce this term, degree of freedoms, DOF. You will be learning both in chemistry and physics with a different perspective, okay? There, degree of freedoms becomes more essential because you will be more essential to apply that in mechanics, okay? Here, degree of freedoms are more essential to apply that logic on molecules. See the difference there, everybody? Right. Now, degree of freedom in simple terms, everybody, is about what is the minimum number of coordinates that you require, right, to express the position or the energy of any substance. What is the minimum number of coordinates? For example, let me tell you, uh, suppose I have, you know, let's say I have exact fit of a tube, okay, for a ball. So now tell me if ball is at position A as it goes into the tube, and now it is at position B after some time. Tell me to define where exactly is A and to go all the way to B. How many dimensions do I require? I would require only one dimension, right? Because it is just going in this direction. That's it. So if we just define this direction, then we can say the degree of freedoms for this ball to move is only in one direction. So that's why it is called degree of freedom is 1. So it is freely going to move in how many directions? Only one direction. Can it go in the Z direction? No. Can it go in the Y direction? No. It can only go in the X direction. So it is only moving freely in how many directions? One direction. That's why the degree of freedom for this one, is only 1. Correct? Let's say second scenario is I have a carom board. Okay. In a carom board, we have coins. And there is another coin here. That typically this is how the carom board would look like. Now from this carom board, on this carom board, you're trying to hit this red one with your striker. So as you push with the striker here, it will go into any of the pockets. So which means this coin, carom board coin, is moving in how many directions? right? It could be moving in many directions, but how many dimensions it is moving, right? If this is x-axis, y-axis, and sorry, y-axis and z-axis like this coming out of the plane. So definitely I can say it is moving between x-axis and y-axis only, correct? So the minimum number of dimensions that you need to define where exactly the uh, you know coin is, that is how many? Two. So that means it is freely able to move in two dimensions. So that is why the degree of freedom is 2. Okay, everyone clear? What if I have, let's say, you know, I have a ball here, right? It is a magnetic coin. Let's say this is a magnetic coin. This entire thing is a magnet. And I let this coin to move like this. Correct. It is moving this way, all the way here, and this way it is rotating. Clear? It is at a distance r. Okay. Now tell me uh, for this particular what is it? This one, a coin. We'll say this as coin. For this coin, how many degree of freedoms do we have? Everybody, think and tell me. How many degree of freedoms do we have?
3.
Three, two.
Because
I couldn't hear. Samyak, tell me.
sir, 3.
Three. Why?
3.
See, it's a plane. It is like this. It's not sphere. This one is a coin. I said both of them are coins. This one is a magnetic coin. This one is a coin as well. So a coin is there. On top of that, one more coin is moving like this.
Sir, but can't it rotate that coin?
Correct. But for a circular, just now I told you, for a spherical part or a circular part, how much is the contribution of circular part?
Yes, sir.
Zero, right? I mean, uh, it is hardly contributing. So you tell me only the contributing ones.
2.
Two. Think again.
It's translational motion because it's on a plane.
Correct. So that means there is x direction changing, y direction changing. Correct? For a particle. But the answer is only one. Tell me why. See, usually what we think is that we have to define the coordinates only in Cartesian coordinates, Cartesian way. It's not necessary. If this is an origin, this point at the center point here, if this is the origin, then, and this is an angle theta, which this particle is moving when it comes to this position, let's say. When it moves to this position, it is making an angle theta. Okay. Can I define the position of this particle with respect to r and theta or no? Correct?
Mm.
Everyone? Coin moves in polar coordinates. Yes, coin moves in polar coordinates. So that's correct. Okay. Now you can see it is a polar coordinate where r is constant and it is only moving this way. So how many coordinates are actually changing now? Only one, that is theta. Only theta is changing. Correct. Thus, since only theta is changing, what is the degree of freedom here? Degree of freedom is only one. So you need to check out always the minimum number of dimensions. Correct. So minimum number of dimensions which you can get where it is freely moving. So degree of freedom is only one. Okay. Now, when it comes to degree of freedoms, in the we understood how it operates in one dimension and two dimension. Now, if the ball is moving in three dimension, and that's what we were looking out for, correct? Here. So if a ball is here, it is moving from this position to this position here. So it is from A, it has moved all the way to B. and here its coordinates were x1, y1 and z1, x1, y1 and z1. Now it is moving here to x2, y2 and z2. These two are the points we have, right? So from here to here, if at all there is a movement of ball or particle from A to B. Okay. Now in that case, tell me how many degree of freedoms does it have? Because now it is moving in 3 dimension. It will have x component, y component and z component. It is freely moving in x, y, z. If it is only a single atom or single ball here, and like we discussed, the rotation is hardly contributing. So in that case, the degree of freedoms will be how many? It will have only 3, and all 3 will be translational degree of freedoms, correct? So which we call it as FT. So FT represents translational degree of freedoms. Okay, everybody clear on that? Right. Now if it comes to similar scenario, very similar scenario now, but this time it is not exactly a circular ball here, correct? Imagine if the particle itself is like this. This is a kind of a particle here, something like an H2 molecule. So for an H2 molecule, from this position, from here to here, it is translating. Okay, so it is translating from a position A here, from A to B. This is how it is moving, correct? Now tell me, when a particle is moving, which is like a dumbbell, this is like a dumbbell now, and if this dumbbell is moving, correct, then how many degree of freedoms do we have? Okay, because when a dumbbell is moving is from one position to other position in space, how much freely does it rotate, or how much freely does it move? One, it can translate from one position to the other position. So 3 dimensions are required. X, Y, Z coordinates are required. Got it? Now, other than that, how many other dimensions do we require? See, now what happens? That, you know, dumbbell can start moving this way, isn't it? As it starts moving, it will keep on moving this way. So it can have a rotation with respect to a certain axis, isn't it? So if a particle is like this, let's say this is a particle, okay, this pencil, because it's a 2 dimension, it is linear. So it is the same particle, like a dumbbell particle here, okay. Now this dumbbell, while it is moving from one position to other position, it can start rotating also. It can rotate and move like this. It can rotate and move. It is coming towards you. It's coming towards me like this. Okay. It can rotate and at the same time it can move. If it is rotating and moving, notice this. If this is Z axis, so it can rotate in this axis. Okay. In motion, when it is in motion, I'm trying to figure out what are its coordinates. When it is in motion, what are the coordinates it can have? It can have one contribution or one component of rotation with respect to Z axis. Everybody, like this, it is with respect to Z axis, correct? This is Z axis. Can I say one contribution will be like this? Yes or no? What is this one? This is like a Y axis, this way, coming towards you. This is Z axis, this is Y axis. So it will have a component which is rotating this way and the other one which is rotating this way. Clear? So two axes got. What is the third component? Now notice this carefully. This is the third component, correct? Because this is the axis now. This is the x-axis. In this x-axis, how is it rotating? Like this. This is the rotation also it can have, correct? So which means with respect to z-axis, this is how the contribution is. With respect to y-axis, right? This is how the this is the contribution which it has, like this. Suppose at any point of time I'm saying this is how it is present. Let's say it is moving in this direction, like this. When it is moving in this direction, the other contribution can be in this direction, like this, and it is in this direction. So can you see two dimension in two different dimensions? It is rotating freely, but in the third dimension it is rotating, but it is not. We are not something able to observe it only, correct? So that means out of the three rotational axes possible, two rotational axes are highly contributing to it. Correct? Two rotational are highly contributing to it. But the third one is not so much contributing. So that's what you will notice. For a linear molecule, okay, total degree of freedoms actually come out to be 5. Sorry, not 5. Uh, it could be first, right? Let me write it now. 3 translational. Okay, it will have 3 translational like this, and then we have 2 rotational. Okay, then what about vibration? Vibration will be like this. If this is a particle, I mean, these two are made up of a molecule, let's say. So the it is like a spring, right? A bond is like a spring. This is how it will keep moving all the time, atoms. So that means there is always a vibration like this between the particles. So the vibration is happening, isn't it, between two particles. This is one vibration. We call something as a vibration when both of them come closer, they go backwards and get back to the mean position. This is called one vibration. So this is continuously happening like this between the particles as they're moving also. See, as it is moving towards, or it is getting translated from one position to the other position, it is also vibrating. So chances are there will be one vibrational rotation. Correct? Everybody, did you understand? For a linear molecule or for any linear particle, correct? You'll always have 3 translational, 2 rotational, and 1 vibrational. So here we find a pattern, everybody. Here we find a pattern. Pattern is for n number of atoms present in a molecule, for n number of atoms present in a molecule, then maximum degree of freedoms, maximum degree of freedoms a molecule can enjoy is equal to 3 times of n. This is the maximum it can enjoy. Clear? But how many actually are contributing? How many are contributing? That depends upon whether you have one particle, two particle, or three particle. For example, if you have monoatomic species, monoatomic like helium, hydrogen plus, lithium 2 plus, correct? Maybe xenon, radon, right? Neon. These are all monoatomic. For monoatomic species, whether it is a positive charge, negative charge, or a neutral charge, as long as there is only one atom present in it. Okay. In that case, right, translational degree of freedoms are 3, rotational degree of freedoms are 0, vibrational degree of freedoms are 0, which you can see the maximum DOF will be equal to how many? 3 only, right? As per the formula also. As per the formula also, it should be 3 times of n. So maximum are only 3, correct? Everybody? Now, notice when it comes to diatomic, diatomic means it is also linear. So if it is linear, something like H2, Cl2, Br2, F2, clear, O2, and any of these diatomic species. So in case of diatomic species, then what is the maximum degree of freedoms it should enjoy? It should enjoy 6 degree of freedoms. But here you will notice that translational are definitely 3, rotational we found it as 2, and vibrational we found it as 1. So from here, in this pattern, can I say that, okay, the number of translational are always fixed, which is 3, correct? And rotational started to contribute now. Now see what happens. If it is a, you know, triatomic, which is non-linear, let's say this is non-linear, okay? If it is non-linear, something like O3, it is non-linear, correct? It is bent. It is not same linear form, okay? So we have something like O3 here, got it? Uh, N3, sorry, O3. Then let's say SO2, correct? We have NO2 minus. All of these have bent shapes. They are not linear, non-linear. So for these kind of molecules, now the translational degree of freedoms are going to be constant. Then rotational going to be 3 now, because now if you have it in a uh, bent shape, now as it rotates, in every axis it rotates, there is a high contribution of energy into it. So yes, in that case, what will be vibrational then? Vibrational has to be the total number minus 6, correct? Everybody, the maximum number is how much? So you can see the maximum DOF in this case, because these are 3 atoms, 3 atoms, and 3 atoms. Okay. So in that case, we can say 3 into 3. How many? 9. So this is the maximum degree of freedoms they should enjoy. Okay. It should enjoy maximum degree of freedoms to be this much. But out of which, how many are translational? 3. How many of these are 3? Then how many vibrational do you expect? So 3 vibrations will, we will expect. Got it? Everyone clear on that? How many degree of freedoms in all the cases? Now, when it comes to when it comes to when it comes to linear species, right? But non-diatomic, that means it could be triatomic and so on. So suppose if you have carbon dioxide, it is also linear. Okay, N3 minus linear, C3, C2O3, C2O3, sorry, C3O2. Okay, this is called suboxide. Suboxide structure will be like this: O, C double bond, C double bond, C double bond, O. It is completely linear molecule. It's a linear molecule. So for these cases, now translational degree of freedoms will be 3, rotational will be 2, but vibrational will be 3n minus 5. Okay, because this total contributes to 5. So this will be the vibrational degree of freedoms. Clear? For any non-linear, this is for linear, and if it is for any non-linear, okay. So if it is non-linear, anything simple as that of water, let's say, okay, like H2O, okay, ammonia, CH4, correct? All of these are non-linear. So if it is non-linear, in that case, degree of freedoms are 3, rotational are 2, and this will become 3n minus 6. So that's how you'll figure out what is the value of monoatomic, diatomic, only linear or non-linear, if you have this, what is the amount of degree of freedoms it has? Now notice, for every degree of freedom, how much is the contribution of energy it has? Okay, so let's see contribution of energy. Contribution of energy, because we are trying to study equipartition. We are trying to give as much equal amount of energy to all the degree of freedoms. So contribution of energy by degree of freedoms. How much is the degree of freedoms in all the directions? So first, for any translational, for any translational uh, degree of freedoms, okay, energy contributing per dimension for one dimension will be equal to, r by 2. This much amount of energy is contributed. Now same thing, if at all I copy the same here, and the second thing what you'll notice is that any rotational degree of freedoms, energy contributed per dimension is also r by 2. Okay, but lastly, for every or for any vibrational degree of freedom, so that should be equal to energy contributing per dimension is found to be only r. Okay, so these are the contributing factors, everybody. This you have to remember it directly. So questions will be asked based on how much is the contribution from each of these cases. Everyone, I hope this part is clear. If anybody has a doubt before going ahead, please do ask right away.
Sir, I had a doubt.
Yes, beta.
Sir, in triatomic nonlinear, the degree of freedom for vibration is 3. But
Not necessary.
if
No. Vibration, degree of vibration will depend on 3n minus 6. It depends upon how many number of atoms we have. Okay.
yes, sir, but for the triatomic nonlinear case, it is 3.
Yes. For triatomic, it is 3.
So at what regions will it vibrate? Like,
Correct. Good question. Check. For example, if you have ozone, oxygen, double bond O, DT bond O. This is how it is present, correct?
yes, sir.
One vibration will be contributed here. Between these two oxygens also there is one vibration. Between these two oxygens also there is vibration. Between these two oxygens also there is vibration. Got it?
Yes, sir.
Vibration does not mean we need to have a bond for sure. It could be an repulsion or an attraction, correct? But it is not necessary have to be covalent bond, isn't it? Imagine
Yes,
like
sir.
if you put three magnets, two magnets are joined, but that does not mean other magnets are repelling, right? They might still be repelling with each other or trying to attract with each other. So therefore, like this, we will have how many vibrations? Three such vibrations you will notice, correct? Right? On this note, everybody, why don't you solve one question? Okay, I think I've written some few of them. Yeah. But anyways, I would like you to do it without seeing. Just I will try to take the examples which are not there in the class notes. Okay. In the notes, I have it for ammonia, carbon dioxide, and PCl5. And I think I took one more. Yeah, SOCl3 and CO2 also. Okay. I took almost all the examples that has been asked in JE. One example, I'll take it just for our sake. Okay. Example, find max DOF, right? Max DOF, translational, rotational, and vibrational DOF for, okay, C2H6 molecule. Everybody try to figure out how much we should be able to get for C2H6 ethane. So what is the first thing we'll do? We'll try to figure out how many maximum number, how many atoms are present in it. So 6 plus 2, 8. So therefore, what is the maximum DOF? What is the maximum DOF now? Maximum DOF will be equal to 8 into 3. So which is 24, correct? Out of this 24, how much is the translational DOF? 3. Rotational DOF? 3. Because it is a 3 dimension, rotation will contribute in all 3 directions. Next. Vibrational, how many we will have? 24 minus 3. So how many beta? 21. So now you noticed 21 वाइब्रेशंस कहां से आएंगे बेटा? हर हाइड्रोजन के बीच में भी वाइब्रेशन होगा. You will see vibration between the two carbons also, between carbon and other hydrogens also, right? So like
Yes,
that,
sir.
there are so many vibrations we can have.
Thank you, sir.
Yeah. Now, think about this factor. Suppose in the same question, if at all I ask you, what is the total CV value now? What is the CV value of this particular question? Within that, sub question is find CV of C2H6, and here consider, okay, vibrational degree of freedoms are active. This is the terminology used. If it is active, okay, usually if nothing is given, we will assume there is no degree of, there is no contribution from vibrational degree of freedoms, correct? Because vibrations contribution only be effective if they are at a high temperature. If the particles are at low temperature, you will hardly see any effective contribution from vibrational. Okay. If that is the case, now I need to find out what is the CV value of C2H6. Then what is that you will find? You know that CV we found, listen, CV we found as 3 by 2 R for monoatomic, correct? Everybody remember that? 3 by 2 R for monoatomic, which we derived it earlier. But if you do the same thing for diatomic, triatomic, can I say that this 3 by 2, we learned it from the basis of equipartition law. So in that case, I can say that F total by 2 into R. So that should be the contribution now, isn't it? But because within the total, again, there is a distinction. So what will I do? I will write it this way. Okay. Translational, in X plus translational in Y, translational in Z, this total, right, by 2 times of R. This is the contribution plus rotation, right, in Z axis, rotation in X axis, rotation in Y axis by 2 into R. This is another contribution plus remaining all are vibrational. So summation of all the vibrational into R. Why not by 2? Because I told you that the contribution for vibration is only R and not R by 2. Okay. So this is what we write it as CV is equal to F into total into R by 2. That is what we are trying to write. This entire thing is the total form. Now if that is the case, now CV will be equal to how many? 3 by 2 R plus 3 by 2 R plus how many are left? 21. So 21 R. So this is the value we should have. Correct? So how many we will have? 24 R. So that is the CV value.
FB shouldn't be 24 minus 6.
Where beta?
Sir,
Sorry,
because
sorry.
as
Yeah. Sorry. My mistake. 24 minus 6. So how many we have? 18. So how much total we are getting? This is 18 R. So 18 plus 3. So how much? 21 R. Still, anybody has a doubt? Understanding degree of freedoms? How much is the contribution? All good? Shauri, are you there, beta? Right. Utsa?
Yes.
Hmm. Now, quickly, right? Since we have written it, you can quickly follow this. See, vibrational degree of freedoms are active only at extremely high temperature, everybody. Okay. So at normal temperatures, we consider vibrational degree of freedoms as, you know, 0. And so the total number of degree of freedoms now will be only from translational and rotational, which is 5 of them. And in case if I want to calculate the CV, I have not done the CV calculation here, but I have to calculate the CV, then CV will be equal to 5 by 2 R, right? Same way you can check out here, the CV value for that same CV, carbon dioxide is 5 by 2. If you are doing it at high temperature, then vibrational need to be considered, and vibrational is 4R. So how much will be the value of CV? CV will be equal to 13 by 2R. Okay. So please check the example of CO2, everyone. Did you get that? Done. C for ammonia, everybody. Check out for ammonia and PCl5. If you have any doubt, let me know. Done? What is gamma? I'll come to that. Okay, don't worry about it. Right. Okay. Now, since we were actually discussing about internal energy, now you can see that internal energy, which is equal to U delta of kinetic energy. Now, kinetic energy can be written as F by 2 RT, correct? F being total degree of F is the total degree of freedoms, correct? So in that case, what we can say, this will be equal to 3 by 2 RT, 3 by 2 RT for monoatomic, okay? And then let's say 5 by 2 RT for diatomic, okay? Without active vibrations. And it could be, see, 3 by 2 RT plus 3 by 2 RT. If at all I do this, how much I will get? Only 3 RT. So 3 RT for non-linear, non-linear particles. Got it? Again, here also without active vibrations. So this is how the value of delta U will be for an ideal gas. So far we discussed the case of ideal gas. I'm hoping that all of you are comfortable with whatever we have studied today, correct? So hope that the revision also should help you. And now if you go back to the original notes, what we discussed about uh, you know first law of thermodynamics, how we got delta U is equal to NCV delta T, and we discussed about what is delta H also, enthalpy, which is delta N into Cp into delta T. This I'll repeat it once again. This is a smaller part. Okay. So in the next class, I'll repeat about enthalpy and all that cases. But from here, you should be able to comfortably understand the terminologies easy. Okay. Hmm. So once you know that, then we will go ahead and discuss the rest of the part. Okay. Hmm. So up to this page, everybody. So 20th page up to this 20th page here. So up to this 20th page, thoroughly read every point. Okay. And if possible, please do practice once deriving everything. Okay. Hmm. Once again.